All right, folks. I guess like in terms of like technical stuff, there were sort of two main things I wanted to talk about. One was, if correlation doesn't imply causation, then what does? And the other is like I wanted to just give you a quick sneak peek on like a future article that I'm working on, which is about sort of software leadership and toxicity, and sort of what I learned about working with software teams from playing competitive online games. Um, Yo, Sudame's, how's it going? It's nice to see you on. So yeah, I mean, like, so this is going to be a stream, like, I guess in three parts. So one, causation; two, leadership and toxicity in online games; and then three, I'm just going to play the forest, and we're going to have some survival game, like, like fighting off, I don't know, like the the creepy pedo zombies in the forest. So overall, I think causality has been a topic that I keep actually revisiting at this point without fully understanding like why it's interesting. And I guess like a big part of it is uh, like if you look at the basics online or at least like read Pearl's books, it's sort of like taken for granted, like, oh, like of course causal thinking is better, but it's not really obvious like how to go about it, how to learn it, what kinds of algorithms can you build with it. And so I did have a past stream, for example, on using Julia, where you could automatically learn a causal graph from a graph. And what was interesting about that stream is that it's sort of like you don't know the arrows basically, so you can know which gives you back to the correlation problem. Like are like is it the clouds raining or is it the raining that changed like the shape of the clouds? Is it was it you taking out your umbrella that made it rain, or did you pull out your umbrella because it started raining? So a lot of these points are kind of complicated, but you know, something I've been thinking more and more about is that when you look at sort of the main people in society making decisions, like generally, like I'm thinking more politicians, they have close to no understanding of statistics. Even I would argue a lot of people in statistical fields have no understanding of statistics. I would say even for my field, machine learning, which is statistics adjacent, people have no idea of the kinds of cognitive biases you can have about like sort of like let's say Simpson's paradox is one where a correlation can be reversed if you add more variables to what you're observing. So, long story short, there's lots of issues with how people think, and it's given me sort of pause here where I hardly feel like these days I can believe anything. As in, unless I myself went and looked at the data and thought about it and convinced myself that, I have an idea of what I'm doing, which for the most part I don't, then there's no point in really believing anything. So that's why I don't watch the news or, listen to experts or anything. So yeah, so, et cetera, et cetera. Now I sound like Joe Rogan. But so I thought like maybe so this is Michael Nielsen. Michael Nielsen is one of the more interesting people I know of on Twitter. He's the director of research at Y Combinator, and he wrote this accessible tutorial on causal inference. So I thought we could sort of quickly go through it and see if there's any interesting ideas here that can give us a flavor as to why these ideas are interesting. So there's sort of three core ideas that they talk about. It's causal models, as in a graphical model. So remember, a graphical model, or really anytime you're drawing like a graph is basically a probability distribution because the nodes are random variables, and then the arrows are basically what's conditionally independent on what, and then you can draw a bunch of stuff. So again, I have a whole other video just talking about this stuff, so you can go check it out if these kinds of topics are interesting to you. So the kind of situation that was interesting here, and I don't know if this is solved, but at some point people noticed that a lot of people that were smoking were getting lung cancer, and so a natural thing to conclude here is to say, well, smoking causes lung cancer. Ooh, pseudomase. Oh, you're subscribing again. Ooh, for 12 months. That's awesome. Hey, thank you so much, man. I appreciate it. You're definitely one of the OGs, and that's hugely, hugely appreciated. So if you're trying to think about, well, does smoking cause lung cancer? Well, a natural thing to do is to say, I'm just going to look at a bunch of people, and if they smoke, then they have lung cancer. But actually, a bunch of tobacco companies, including actually Fisher from like the Fisher distribution, like one of the fathers of statistics, actually claim that this is bullshit. And actually, it's not smoking that causes lung cancer, but it's some sort of hidden factor that makes you more likely to smoke that would also make you more likely to have lung cancer. So you may think like this is like you may think again this point is bullshit, but even like regardless of what you think, disproving this hypothesis is kind of challenging. And I think, well, like the causal calculus will help us sort of figure out how to go about these problems. All right. So here, so remember I said, like you can think of nodes as being random variables in a probability distribution. So for example, here they're saying, okay, we have x1 and x2. So x2 could be a two outcome random variable indicating the presence or absence of some gene that exerts an influence on whether someone smokes or gets lung cancer. All right, so this is the sort of mystery gene that would make you more likely to get lung cancer and also more likely to crave smoking. So that's x2. And then so x4 is, do you get lung cancer? Sure. What's x1? Other potential dependencies. Okay, so there are basically some other dependencies that we may not fully understand. So X3 is, do you smoke or not? And then X4, did you get lung cancer? X2 is the mystery gene, and X1 and X5. So really the point is that, this is sort of the simplest graph that encapsulates what the Surgeon General was saying in the US, but also encapsulates like what critics like tobacco companies were saying is true. So both of their beliefs can be encoded in the same causal graph. So for the notion of causality, it makes sense we need to constrain the class of graphs that can be used in a causal model. So it makes no sense to have loops in the graph. Uh, yeah, so at least like I guess like with this group, like why does it not make sense? I guess like his feedback loops would just make things either go to one or go to zero always. Yeah, and so acyclic graph really just means, so really when we're talking about graphs here, we mean an acyclic graph, as in starting from a node and then going out by its neighbors, you can't come back to it. But really, it's just a complicated word for a loop-free node, and this is what Nielsen is saying here. All right, so intuitively, what causality means is that for any particular xj, the only random variable which influences the influence are the parents of xj. So the collection x parents of j of random variables which are connected directly to xj, and we show, so for example, the parents of x4 are x2 and x3. So what this means is if you say x2 or x3 cause x4, that means that it's funny like the all you need meme. I wonder, I mean, I keep waiting for this moment when causal inference is going to end up being something. Yeah, you're right. I think graphs are all you need, or DAGs is all you need. Uh, I think in GNNs, like, do they have like? I mean, yeah, like I think they're also like like they're also directed a cyclic graph, so you just like propagate outwards. I wonder if there's ones with cyclic. I mean, no, like you'd have like an infinite inference, right? Like if you're just like, oh, update this layer based on this layer, and then update this layer based on this layer. Although I don't know if infinite inference maybe works. Who knows? Um, all right. To denote the subset of random variables from the graph. So one way to define causal influence would be to require that xj be a function of its parents. Okay, so a function of its parent, and then fj is a function of the random variable j, right? So we're just indexing the function by itself. You could also make the function itself take two parameters, like the random variable and then its parents, and that way you just need a single function that operates over a larger space. Okay, so specify the causal model's joint probability distribution is a product of conditional probabilities. Yeah, so the probability of a bunch of random variables is the product of its probabilities conditioned over its. So I mean, this is, I'm not going to go over, like this is just like basic probability, and we can go prove it some other time. Uh, but basically, you can imagine, like I guess like a few examples help. Like just basically, the whole point is like once the parents are known, then you don't need to know anything about any other nodes, right? So if you know x2 and x3, then you can fully determine x4. And having information on x1 and x5 isn't helpful. What is interesting is that if you can directly observe x1 and x5, but you can't observe x2 and x3, then that's when you need sort of the full graph. But given that you know the values for the parents, then you don't need to know the whole graph. All right, so the probability of given cancer, given that you smoke, is greater than the probability of cancer given that you don't smoke. Yet if the additional genetic factor is reversed. Yeah. So basically, we know like you don't need to do complicated statistics. Like let's say we've even anecdotally observed, like talk to people that you know, and then count number of people who had like lung cancer and count how many times they smoked, and then you can realize like wait a minute, like if people smoke, then they're more likely to have cancer. But this is where Simpson's paradox comes in, where if you condition on additional variables, as in like this specific gene, maybe you can actually reverse the correlation. So problems for the author. Okay. So I've been using terms like causal influence somewhat indiscriminately in the discussion above, so I'd like to pause to discuss a bit more carefully about what is meant here. All the arrows in the causal model indicate are the possibility of a direct causal influence. This results in two caveats on how we think about causality in these models. First, it may be that a child is actually completely independent. Okay. In a causal model like this one, it is possible that the outcome of cancer might be independent of the hidden causal factor. Yeah, so this is a good point. So we're not saying like this sort of graph is independent of your beliefs, as in it may still be the case that no hidden factor exists. It's just that we're trying to see how likely this graph is, and if so, what's the strength of the arrows here. So we'll look at the most imaginative belief underlying the. So we'll introduce the concept of causal conditional probabilities. So the notion of ordinary conditional probabilities is no doubt familiar to you. It's pretty straightforward to do experiments to estimate conditional probabilities, such as probability of cancer given that you smoke, simply by looking at the population of people who smoke. Yeah, so this is exactly what I was saying. For the purpose of understanding the causal relationship between smoking and cancer isn't the quantity we want. As the tobacco company is pointing out, there might be a hidden genetic factor. Okay, sure. He's just repeating himself. So, so what we'd really like to do in this circumstance is a randomized controlled experiment. So again, randomized controlled experiment is the best way to determine whether something is causal or not. So you basically, let's say, force a bunch of people to smoke that don't necessarily smoke, and then take a bunch of people that don't smoke and just don't do anything, and maybe people that do smoke and tell them to not smoke. Uh, and then you just count the outcomes. But you can't do this. Like there's no way this would get approved anytime today. Maybe in the last 10 years, this wouldn't get approved. But so how do we do this, right? So what can we do when we don't have when we can't do a CRT? So another example is COVID, right? Like we don't necessarily know like whether lockdowns help or not. Like let's say when this started a year ago, like we're not too sure if they work or not. We can't do a controlled randomized experiment, so can we potentially use something like the causal calculus to be able to determine whether lockdowns are a good idea or not? So he introduced a conditional causal probability, the probability of cancer given that you do smoke, which is the probability of cancer in this hypothetical word. So the probability of cancer given that we do smoking. Someone has been forced to smoke in a given randomized experiment. Okay. So I guess like we're trying to look at, pretending that we're in a virtual world where we can do inferences like this and then see what we can do. So, as I've indicated, this seems like a rather useless thing to do. But what makes it clever is, although it may be impossible to do one, was able to establish a set of rules that such conditional probabilities should obey. And by making use of the causal calculus, it turns out to do something to be possible to infer the probabilities of something such as P of cancer due smoking, even on a CRT is impossible. Okay, so basically we can do CRTs on piece of paper. So now suppose we introduce an external experimenter who is able to intervene to deliberately set the value of a particular random variable. All right, so you can come and you can influence the outcome yourself. So you can change the value of random variables. The experimenter can override the causal inference on that variable. So this is equivalent to having a new causal model. For example, so you're an experimenter. Oh, I see. And you're going to change the value of x3. Once the value of x3 is known, the value of its parents is irrelevant. Remember, conditional independence. And then, but it still influences x5, right? So this is what we're doing here. We're going to make an influence in our diagram and see if it impacts anything. Okay, just repeating what I was saying here. Okay, so more generally, you're gonna by making this kind of influence, you're gonna get a new graph where the random variable that you changed, you are basically gonna delete all the edges that are pointing from their parents, right? So they call this the perturbed graph. Sure. But again, like the main idea here is that conditional independence lets you simplify the graph. That's sort of the main idea here. So our aim is to use this perturbed causal model to compute the conditional causal probability of this given do this. So notice that xj also figures here, right? So, and that's because that xj didn't actually happen. We're pretending like it happened and then trying to see if this lets us make any claims about the joint probability of the whole probability distribution. Remember, we're doing CRTs in our heads. Since we have fixed the value of xj to be xj, as a result, we have so the probability of xj of x1 given xn divided by the probability of xj given its parents. Okay, let's think about this expression for a second. So we're saying, like, generally the way you would do something like this is that you would just have the probability of xj, right? Because we're setting it. But here instead, what we're going to do is that we're going to say, well, but like, let's say, so how do we think about this? Because the parents, the arrows are being deleted in this case. So let's see. So probability of x1 to xn, and it looks like this includes xj. Otherwise, they would have omitted it explicitly or put in like a dash on top of it. And then you're saying probability of xj given the parents of xj. All right. So then in general, when we're trying to probability of something given do x, it's equal to the probability, joint probability of x and y, um, divided by the probability that xj happens given the parents of xj. The expression one can be viewed as a definition of causal conditional probabilities. Yeah. Okay. Okay. So let's get back to our example with smoking. So what we want to do is compute probability of cancer given do smoking. Okay, let me just draw some quick. I think I'll simpler. My tablet is dusty, pseudo was not a good sign. Saj, I know. Yeah, it's a Wacom tablet. One of our services is down. God damn it, Microsoft. Okay, so let's do this, and then we do this. Okay. So what we're saying now is we want to look at. So the probability of cancer given do smoking, right? So it's sort of the hypothetical word where we force someone to smoke. So what this is going to be equal to is it's equal to the probability of cancer and smoking divided by the probability. So in this case, it's going to be the probability. So yeah, so it's going to be divided by the probability of smoking given hidden factor, right? So, but what do we have, right? Like, can we actually compute this thing? So one, this part of the expression Not really, right? Because we don't even know what the hidden factor is. And here also, better emote. This is Sage. All right, what are you showing me? I'll take a look. What's up with smokers looking Arab all the time? Yeah, so as far as the probability of cancer given smoking, well, all we have is the probability of cancer divided by, so conditioned on the probability of smoking. Right, so this we can do with counting. And this we can do with counting. And this we can do with counting. So all these we count them, right? Like how many people have cancer, lung cancer in the world, how many people smoke, and this we have as well. So actually, no, this part is fine. Like this part we can compute. And it's this part that we can't compute because obviously we don't know what to condition it on. Like we don't know the probability of the hidden factor is. Like that's just silly, right? Like we have no idea. So we can actually write out the basically the formula for conditional probability or Bayes' law in this case. Okay, so now that we have the basics out the way, let's keep going. Um, okay, so he's saying that all is not lost, so we can still do something like a skip connection. Yeah, I guess like in the sense that like I don't know, like because even no in the case of in the case of this one, well, in the case of skipped connections, you still know what the thing is, right? Like it's still just a layer with a bunch of weights. Like it's not sort of like this unknown entity. Okay. Oh, interesting. Okay, so even though we can't do this, what we can say is we can like this we can't do, but what we can do uh, is basically look at probability of cancer given due smoking and say is this equal or not to the probability of cancer given uh, not due smoking. Right, so this is a bit more interesting, right? Because like this is really what we want, like what we don't care about the actual number, we just care, is it, are you more likely to get lung cancer if you have, so I guess what we care about is the like the equality or inequality of it, right? Okay, all right, this is interesting. Suppose we define the causal capacity between x and y to be max of h as a mutual information. I see. So, I mean, I'm not going to do this exercise, but really what this is trying to say is that like if you set if you set the value of any one of these variables, so let's go here. If you set the value for any one of these variables, you're essentially transmitting information to the neighbors, but you only transmit information to the neighbors on which you have a causal relationship towards, which just sort of makes intuitive sense. So I'm not going to go ahead and prove it. Not that intuition is necessarily useful for proving stuff. Just, yeah, just so we can keep going. When you say something like event A causes event B, what does that mean? So returning to the smoking cancer example, that essentially means that we want to say probability of cancer due smoking is greater than the probability of cancer. Oh, I see. So okay. So it's not it's not this that we can do. It's actually P of cancer given due smoking We want to say that this is greater than P of Cancer. So suppose X and Y are random variables in a causal model such that Y, you know, so basically probability of cancer given that you do smoke, is this greater? Like, is this always true? Basically, are we, like, I think his question here is this true? Like, is this intuition? Oh, Pseudomaze, I want you to think about, if you don't mind, because in the next section, like I said, I want to talk a bit more about like management strategies and toxicity and how to work with other people. So if you have any questions about any of this, like please let me know. Like if you've worked with people, if you haven't worked with people, I would be super grateful because it would be a good segue for me to share some stories. Okay. Okay, I think here what he's asking is how do we learn these things? Thank you for the subscribe. I appreciate it. So this leads me to, let's see. Oh, Nuvik, nice to see you on. So yeah, let me know if you have any questions. I'm talking about causality. I'm going to talk about like toxicity and working with teams. But juicy experience. Okay, so he's asking, is there any other way of formalizing stuff by followers? Yo, Sudame, can you ban the guy who just typed? Yeah, perfect. Thank you. You're the best. Okay, so this is, I think, sort of to me, this was the most important point here. Make me famous, daddy. Okay, so sum over conditional probabilities. So okay, all right, deseparation. So deseparation, I think, is similar to conditional probability, at least in intuition. So let's take a look at it a bit. Directional separation is lets us inspect the graph of a causal model and conclude that a random variable in the model can't tell us anything but the value of another random variable in the model. Yeah, so basically there is no causal relationship. So yeah, so again, so here. So knowing X tells you something about Y, right? Even if you don't know what this thing Z is. So they're not deseparated. However, in this case, the cause, like in the following causal model, X and Y don't give us any information about each other, so they are deseparated. Yeah. Whereas here, like if you know something cause, okay, so us do the intuition a bit. So something causes something that causes something that causes something. If you know what the first thing is, it's likely that this is also going to be true, right? You can figure out this sort of relationship. In this case, let's say two things cause one thing. So, for example, let me think about this. I'm Lebanese. Okay, so that's one X. Two, Y, I'm a computer scientist. And then this is, I left my job at Microsoft, for example. So what we're trying to just, so do you want me to add a bot to notify people on the server when you are streaming? That would be nice, but like something non-spammy. Like I don't want to give a notification to here everywhere, unless you think is it appropriate? Because I feel like I don't want to be. I don't know actually, because I guess if people are joining the Discord, they do want to hear me talk. So yeah, fuck it, why not? That would be nice. Okay. So whereas here in this model, it's like we're saying something causes two things at once. And so in this case, if you know that X happened, you can know that you know something about Y as well and vice versa because you know they have a common ancestor. Okay. So sort of the intuition again. So if two things are deseparated, that means that they are conditionally independent. And I think you can do this by looking at so you can do this solve problem. It's like the only definition you have is this, right? It's sort of the parents, like this definition. And working with this definition, given that you know what the common parents are, you can sort of reverse engineer it and figure this out. We can do one for fun if that's helpful. Yeah, fuck it, why not? I'm gonna embarrass myself. Let's do it. So let's say, for example, so we know that P, uh, I'm just gonna write down the definition, xj, sorry, I'm gonna write down this definition. So P of y equals y, given do of x equals x, is equal to P of x equals x, so y equals y, divided by the product over the j indices of P xj equals xj, given the parents of xj, right? So this is our expression. So what we want to show is some two things are deseparated. So let's take a look at this graph, right? So this is our graph. So what we want to prove is that P of xy, so basically the theorem is that P of xy is equal to P of x times P of y if x and y are d-separated. All right, so let's take a look at each one. So the probability of, so I'm going to call this thing z, but how do we remove it then? Probability of x and y given z. So is that what we're doing? So if we have the probability of z given do x, so this is going to be equal to the probability of x and z divided by the probability of z given x. And the probability of z given do y is probability of z y given p of z given y. Right? So the probability of, so please don't use everyone. It is spam, right? I think I've seen other servers use it. I'm not a big fan of it. Like, I don't know. Yeah, no, I'm not a big fan of it. So what else do we know? So we know that the probability of z given do xy, right? So we know that this is equal to probability of z xy divided by the probability of z given x and probability of z given y. And so what I'm thinking now is that the rest of so these are sort of the definitions we can work with, and then some algebra over this. So there's some property on this that I'm missing. So what is it? So if I do both things, then, oh, I see. So really what we're trying to say is P of z given do of xy is equal to the probability of z given do of x, which is equal to the probability of z given do of y. So then if we set this up, so we have probability of z xy, probability of z of x, z of y, which is equal to the probability of z of y, probability of z given y. which is equal to the probability of z of x and probability of z given x. And so let's multiply some stuff out. So I want to multiply everywhere by probability of z of x. So then we're going to have probability of z xy, which is going to be equal to the probability of z of y times the probability of x given y, which is equal to the probability of z and x times the probability of, no wait, it's going to be z given x and z given y. Okay. So now what happens here? So we need to get back some formula like Bayes' theorem, I feel, is what this is missing. So first off, is this true? Like just by itself? Z of xy. Maybe later. Like, let me just keep going. Yeah, so I'm suspecting here, like, just, some magic. No, fuck it. I'm copying out. I think like Bayes' law, we need it somewhere here. Then I think it's proven. So what are we missing? Oh, so the probability. So let's just take a look at this part for a second. So we have probability of z of y times probability of z given x equals the probability of z and x times probability of z given y. Right? So in this part now, so the probability of z given y divided by the probability of z given y is equal to the probability of z and x divided by the probability of z given x. Right? And then we recover the definition of, so the probability of z given x is equal to the probability of z x divided by the probability of x. Oh, I see. And then by setting basically px is equal to 1 and go in reverse. Yeah, we proved it. Oh, sorry, it was blocked. So this is the whole proof. That was longer than I expected, actually. Whatever. I haven't done this kind of stuff in a while. I sort of miss it. All I do right nowadays is model.fit. Model.fit. All right. All right. So this is an interesting case, right? So remember we talked about how if let's say generally in this case, so let's say let's say so knowing x gives you additional information about y even if you know z because you don't know what this variable is and this variable has an impact on y. We're wise to be cautious because x and y can really tell us something extra about another given a knowledge about z. So Bergson's paradox. Oh, I see. So this is another interesting case. So Let me explain this example briefly. So let's say colleges are assessing you on two things. Like one is your grades, and two is, for example, like a coding screen. So it seems that like in some cases you would expect people to do very well in the coding screen to have very poor grades. Like let's say given that this is not the topmost college, say this is like an average college. If those are the two things you're scoring on, then it's extremely likely that if someone is really good at the tech screen, then you can make an inference that they actually have bad grades, and vice versa. If they have good grades, then you know that they did pretty badly in the coding screen, because if they did well in both, then you would expect them to apply to a better school. So these are the kinds of weird paradoxes in stats which make me really skeptical about believing anything that I read. That's why I never trust headlines that say something like, I don't know, cucumbers cure cancer. Actually, like this is an exercise to both of you, Nuvik and Pseudomaze. So let's say, and the three other people watching. So let's say I make the claim that I noticed that in Korea, uh, I'm giving away the answer, but it's okay. So let's say, like, I'm making the claim that Koreans don't get stomach cancer a lot. So pineapples can get rid of floaters, according to some academic papers. Yeah, why not? So yeah, so again, I'm making the claim that if you're Korean, you're less likely to have stomach cancer. Is this like a nonsensical statement, or is there something interesting going on? So one way to say it, to think about it, is like, well, like what's in the Korean diet, and let's say fermented cabbages. So kimchi is very popular. So then, should you be eating kimchi to reduce your risk of stomach cancer? So this is the kind of stuff I think that this, like again, like this argument sounds weird, but let's say, like, remember the news, right? Like omega 3 vitamins, uh, I don't know, like walk, like basically all. So omega 3 vitamins, pineapples reduce cancer. So how should you think about? So H0, Koreans get stomach cancer equally to other countries. Test for this. Sure, yeah. So you could basically do a count, and count like just and then divide by the population, right? And then you can get some sort of estimate for whether H0 is true or not. Unlabeled vertex W, and finally we choose Z equals W. I connected for informationally separated and informationally connected. Yeah, like what's up with the D, right? Like I think this is something that's not explained very clearly. I don't think I showed this to you, but like they have like a clubhouse style feature. Dude, like that company is GG. Like they probably thought they were on top of the world, but like at this point, Koreans getting stomach. Do we need to understand nutrition science? I mean, generally, I think understanding the core science lets you then build a graph, and then you can sort of make inferences about those graphs and see what is probably true given your domain knowledge. But I think the sort of promise, like part of what makes supervised learning or machine learning so interesting, is that you don't need any domain expertise. Like as long as you formulate your problem as a supervised learning problem, like it all works great and fine until it doesn't, because people complain. So okay, regulators want stuff to be interpretable for banking, for like for a lot of, for rentals, for any sort of government decision. They have this need to be able to debug things and change them and debias them. And so this is where some of the science is coming about. But again, like when it comes to like it's never going to work at the same scales because doing this kind of analysis means that for every new question that you have, like you basically need to sort of sit and think about it and have an understanding of how these techniques work. But I'm not very optimistic about these sort of techniques becoming standard part of a programmer's toolkit, at least not anytime soon. Yeah, Clubhouse and that poor company. I think like I realized with Clubhouse that I would whenever I'd use it, I would advertise stuff on Twitter, and then I sort of need to record it manually if I'm recording and then post it. And it's like too many fucking steps. Like the discovery sucks. Like I never went on it and serendipitously found something I cared about. Like the only interesting people doing interesting stuff with it were, like I don't know, like Ben Horowitz and stuff like, and it's cool, but eventually like they'll get bored of it, and like I can only listen to them for so much, and I just feel like YouTube is just a better experience for me. I don't know if this is just me being a boomer, but it's just I realized like it was definitely a fad as far as I'm concerned. So Shivan93 is asking, so can you ask an ML algorithm how it came to its conclusion, or is it a black box? Detecting diabetic retinopathy, asking the algorithm how did it determine it has this level of deep represent. I don't know what you mean by DR. Oh, diabetic retinopathy. Okay. So I think that there's a couple of approaches, it seems, to uh, basically make models interpretable. And I think the main one I've seen is this notion of counterfactuals, which sounds complicated, but is actually a very simple idea. And so let's say you're trying to figure out like if your algorithm is racist. So one way to do it is you could basically say, I'm going to have one version of the algorithm where race is present, and then another version of the algorithm where race is not present, and do the algorithms change substantially in their results. Another way to do it is to, for example, look at a person and basically do an intervention where, like, let's say, I'm Arab, like, strategically make me, American. And then you can determine from that, like, did the outcome change for me in the data set? Like, or does the algorithm do different things? And if so, that's a good way to debug it. Otherwise, in Vision, I've seen saliency maps, which is basically asking a network to give you the highest activation pixels. And that gives you some sense, or even segmentation maps with attention, which give you some semblance of where stuff is important. And you can do similar stuff with attention networks in general, like where the highest attention between labels. Give it two labels that you think shouldn't be correlated, and then see how correlated they are. Say you give it Arab and terrorist, you don't want those two things to be correlated ideally. So there's all sorts of tricks like that, but there isn't, as far as I can tell, something that's just like, look, here's this thing. You can put it on top of your algorithm, and look, it's no longer going to be racist. I think this is just a dream at this point. And I think that's why right now the more modern approaches I guess I've seen for bias have been stuff like model cards, where you ask yourself a bunch of questions about how the setting in which the algorithm is deployed, or how it's used, or how it's trained, or who trained it. But fundamentally, given that these are like process heavy solutions, they don't necessarily, I think, scale as well, which is why I think people are less inclined to want to adopt these kinds of ideas, or maybe just out of convenience won't do them. But certainly, I think if you can get to a point where it's just like by default, you say model.fit and model.add, don't make this racist, everyone would use it. But it seems that that's not really feasible right now. So I think it's more of an awareness of the literature, an awareness of all the ideas, wanting to engage, etc. So all this takes time and is difficult. So like an ML has a conscious, it has metacognition to see that it has a bias. No, I don't think it has metacognition. I think at best what it has is you give it something to optimize and it optimizes over it. Uh, yeah, I mean, like that's one solution. Like basically, like it's a, I'm not going to comment too much more about bias. I don't want to get canceled. Uh, I think these are tricky questions to answer. So I'll delegate it to experts who actually know what they're talking about because I haven't engaged in this literature for very long. Uh, all right, so let G be a graph and XY be disjoint subsets of vertices in that graph. Then X and Y are D-separated given Z and if only given Z, if and only if all causal models on G, the random variables corresponding to Z, X and Y are conditionally independent given Z. Okay, sure. Prove the above theorem. Okay, so you can ignore observations if things are D-separated. That's great. Yeah, so suppose that we know that Y is D-separated from Z given W and Z, then the probability of Y and given W given do X and Z is equal to probability. Okay, so yeah, so we're just ignoring observations here, right? So interestingly enough, we ignored Z but not W. How come? Oh, because we deleted the graphs of G. Okay, yeah, sure. Like we deleted the arrows pointing like we deleted all the arrows pointing to it because we know what it is. Okay, sure, yeah, that makes sense. All right, so what do y'all think? Does smoking cause lung cancer? I think this is but you see what's so painful about this? Like it feels like such an obvious causal relationship and it's just like okay, it's like let's do this information dump so that you can get it. So when can we ignore an intervention variable entirely? So okay, so when can we ignore a do? So if y and z, so what's zw? Doctor in his 50s. I think that was actually one of the theories for it. It's like, well, what if, like smoking lets you, like the reason you cough is because you can clear out like all the toxins from your lungs. Or maybe if you smoke, you're going to be more attractive, and have more sex. And that's also correlated with like a higher likelihood of living longer. So all sorts of weird arguments you can construct from something like this. I think though, like when the Marlboro man died, that's like when people started to seriously revisit this because like that whole like smoking is attractive. Now I don't think it's considered attractive. I think it's considered disgusting. For example, in California, but in France, for example, I think yeah. So smoking makes you cool, and that means you're healthy. Exactly. So let's see if W denote the set of nodes in Z which are not ancestors of W. The nodes of Z in Z which are not ancestors of W. Okay. And so okay, there's a lot of terminology here. So GX, the perturbed graph, edges pointing to X have been deleted. All edges pointing out from X have been deleted. Okay, so all edges pointing to from W deleted, X deleted, and from Z deleted. Okay, sure. It's kind of interesting notation actually. You see, this is what the fuck I mean. Like, ugh, I can't. Like, what do you think? Like, let's say you didn't know anything about this, right? And then, I don't know, you're sitting and you're vibing with your friends and you're smoking, and some dude's like, look, I have like this new causal calculus. Yeah, like, I think this has been my impression every time I revisit causality. Like, this is my impression of it. It's sort of like, I think I called it a tool of meditation in the Great Stagnation because this is what it feels like, right? It's like you sort of think about stuff and it feels really important and profound, but then you realize you have more questions than answers, and maybe that's really what meditating is about. And then I realize how small I am in the universe and how knowledge is fundamentally distorted and stuff. Okay, sure. But then you could also have the hidden factor also pointing to tar and lungs, right? Like this is sort of where this gets tricky, or it could be another hidden factor also. No, dude, you should like don't feel sad about your thesis because I think you'll realize very quickly, like once you start working full time, you have very little control over your time and your interests. Like it's sort of like I don't know, like your skip reads like a Business Insider article about how something's really important, and then all of a sudden, like that's what you have to be interested in, regardless of what you're interested in. So I'd say, I mean, no, like it's I don't know, maybe I'll talk about this some more with leadership and toxicity and stuff. But I feel like, for the most parts of my life where I felt sad in general, it's sort of counterintuitive to say it, but it does feel like being sad about stuff makes you lose out on a lot of time and makes you lose out on basically stuff that you could do to make your life better. And so from, like I don't mean to be very broy about this, but for me, I felt like generally there's a few like things that if you lack, it's very hard to be happy. One is like, you're broke, like very hard to be happy. Two is you have very little control over your free time because you feel like you're constantly in a sort of a grinder and you don't really have control over your time. Three, I think, is seeing the sun. So that's why if you live in a cold area that has no sun, I would not recommend it. Move to a sunny area like Miami or California or the Middle East. And then four, I think, is like having like a partner. So just like I think dating is probably like a I haven't seen the sun for over a year. That's a big deal, right? Are you like you're taking vitamin D pills and shit, right? Who needs the sun, right? All you need to do is take this pill. I think this is such BS. Like I don't think we're meant to function in like long winters. It just sort of gets to you. We generate from the oil. Well, I funny joke. Like actually, oil is solar power, right? Because like the way oil is created is by the the Earth crust storing solar energy. So you're being environmentally friendly in Saudi all along. Ah, it's okay. I think it's like so. I think it's interesting though. So the thing they're talking about here um, is if you let's see. So here, so basically, you have a causal graph, and what you're then going to do is you're going to look at specific random variables in the graph, and you're going to delete edges from it into a node or out of a node, and then think about stuff, right? So basically, draw out a causal diagram, delete ingoing and or outgoing edges, and meditate. I think this could also be an older article too, by the way. So I don't think maybe Mathtrax wasn't available. So the probability of y given to x is equal to probability of y and z given to x. Okay, yeah. So we're conditioning on something that we know to be true, which is that the person has tar in their lungs. Okay, so then he applies rule 2, rule 3 a bunch of times. Okay, so then at the end, the very end, okay, what are they saying? So 47% of the population are non-smokers with no tar in their lungs, and 10% people get cancer. 47% are smokers with tar, and 85% get cancer. 2.5 are non-smokers with tar, and 5% get cancer. 2.5% are smokers with no tar, and 90% get cancer. Oh, interesting. I liked it a lot, actually. I think the main bad thing about working for the government is that you don't get paid anything. It's like, I think my rent was like, it's a bit more than what I was actually making. Uh, so from that point of view, I wouldn't recommend it. But at the time, I had a really great boss called Rob Woodoff, and he had, I think, just went through Y Combinator, and he was starting the very first like data science team for NASA. It was great. Like we were doing stuff like being able to predict like network security vulnerabilities from like logs or like stuff about like astronomical observations. So it was just at the time the team wasn't doing any data, and so the team acted as a form of consulting team to do prototypes for everyone else. And it was cool because by the time the summer was done, we had 5 interns, and those 5 interns each like had a prototype project that became a full product. So I think, yeah, I think Rob was insane. Like he just was really, really good at just getting shit done. So I was hugely impressed. It was fun. Like he was a good hacker. Like I felt like he gave me a good love for programming and just like learning stuff very quickly and doing prototypes and stuff. So we were constantly building small stuff. Yeah, that's what I was saying. So maybe there's some other factor that causes star in the lungs. Yeah, and I guess like I mean this is sort of the I think the bitter truth here, right? And that you build a causal diagram, people may disagree with your causal diagram, and so it's sort of like this continuous exercise for you to improve the model, and then for it to get to a point of complexity. So you have shared Microsoft story. I don't know if you are comfortable talking about it again here, but what other stories that you had during work that made you fix your prior of something greatly? What do you mean by that? Like fix my prior? Like when I changed my beliefs, basically? Yeah, let's see. I mean, let's think about it a bit. So I think like the main one was like I wasn't like very useful, I think, in general during my time there. And I think I sort of learned it the hard way. So part of it is I think Microsoft like lacks a certain, I think, kind of intensity or I think proactiveness when it comes to how you should do stuff. As in like there's no like concept of boot camp. There's no like real method of coaching. It's more that like if you're doing a good job, people tell you good job. If you're doing a bad job, people won't tell you anything. I think that's not very helpful. So for me, for example, the main things that I felt I struggled with were, uh, if let's say, for example, you're in a meeting and you feel useless for a very long time, the common piece of feedback is, take lots of notes. I don't think this is good advice. I think what you want to be doing is sort of taking, like, documenting unknown stuff and then confirming whether that stuff is true. So you need to be a bit proactive in that the information that you summarize needs to be valuable for others, for them to value you and come to you as a reference, so that you're not just sort of the guy tagging along in meetings, but you're actually making useful decisions. I think the main thing I think is that, like, well, when you're working at a bigger company, you're working with a lot of people. So each project will have their own tech leads, their own PMs, like a whole bunch of people. There's a lot of PMs at Microsoft in general, more so than Facebook, for example, where I haven't met all that many PMs. Um, yeah, for exactly, like if the information is just basically something that a machine learning algorithm can do, then you're not really providing as much value as you think you are. It needs to be decisions, like this is what we should do, and here's why we should do it. And even if it's wrong, it's still better than being very passive about it and not saying anything. So I think, like, the other thing, it's like you sort of need to be very, I think, clear about what you're doing and why it's important. So a big part of it isn't just coding. It's like documenting what you're coding on, why it's important, who's using it, are they using it, do they like it, why don't they like it, why do they like it. So in my current job, for example, part of that is easier because it's an open source project. So fundamentally, everything I work on is public, which I like, and forces me to, step it up. But if everything is internal, if you're only sharing it with one or two people, you may not necessarily get the kind of quality that you're getting. Not because people don't want to give you feedback, but because maybe they feel it's too nitpicky or it's hard to improve it. Which gets me to my final point is that, like, I think a lot of guys, especially I've seen do this, is sort of have this almost like childlike attitude when they're like, "Oh, I want to be mentored by someone." And in hindsight, it's such a waste of time because, like, no one wants to mentor you. Like, if you email me, telling me that, here's, so you're like, oh, what should I do in my career? I'm like, I have no idea what you should do. Tell me what you're doing, and I can tell you if it's useful or not, whether I like it or not. Give me feedback on something specific, and I can help you. So I think getting specific feedback and acknowledging that you are yourself responsible for improving your life and your career, I think is a very bitter pill. I think with racial bias, I think for me personally, not so much. I have seen instances of people interrupting others a lot, especially if the person, like, I think women definitely were getting interrupted more. However, I do think, like, I mean, I try to give people the benefit of the doubt. I think most people are friendly. They try not to be assholes on purpose. And generally, if people are repeatedly assholes, I think it's difficult for them to be in the environment for very long, or people just won't want to work with them. So they end up, like, sort of in this trunk where not much valuable work is happening. That said, I do think that, I think the rules of being playing nice are enforced more heavily on people that are more junior, and I have noticed that executives in general tend to interrupt you more, tend to be more toxic, and I think that's because they think it's like, oh, like, it's more you're being a leader, or so you're, it's like whatever. But, I think a lot of it was just giving them, like, a free pass because they were the boss, and I think people realize this. It's like, all right, yeah. So this is the philosophical thing. So the rooster crowing is what makes the sun rise. That's interesting. Like, thinking about building causal models for the laws of science. I have been bullied because someone thought I was an American. Then, when he knew I wasn't, he started harassing me during IBM conference during my undergrad. The funny thing is, his parents are immigrants, but he hates non-Americans because he thinks they are here to steal jobs. So I think like the argument around immigration, I think people sort of talk each other over it. I think when it comes to low skilled labor, it does seem like it is zero sum, but for high skilled labor, I think not so much. So I generally think it's a bit unfair that if you're sort of like in a non-zero sum discipline, making a lot of money, if you want to tell people what their recruitment policy should be when they're telling you that this is influencing us in some way, that's kind of a bit unfair, I think. But yeah, it is definitely complex. I think, yeah, at the very least, it's a complicated question. But I guess in your specific experience, like, it's a bit annoying, I think, when you get into situations like this. And I don't have a good answer to how to deal with it. I did have a dude once call me a terrorist, but he was also, he barely spoke English, which was kind of funny to me. But so it wasn't it wasn't a white dude being racist. But regardless, I think when I like he's a CEO of a startup who harassed an undergrad for no reasons besides he's an American. Yeah, that's kind of a loser thing to do. I think that's like it does. It should have better things to do, like go make money, for example, than harass like undergrads. All right, I actually like this survey lecture. I want to show it to you in a bit, but let's go back up and let's take a look at what he meant by rule two and rule three. So when can you ignore an intervention, and when can you ignore a variable entirely? I think this is a. Oh, sorry. I think this is a really neat summary, actually. So let's just take a final look at this, and then I think we can go to the next article. All right. So let me just make this bigger. So remember, so here we're saying, for example, that two nodes, or they could even be sets of nodes, by the way, y and z are deseparated, as in think of it like a causal conditional independence, given nodes w and x, where we've deleted all the edges from the coming from parents to the node. So like read this like from the top, right, from the parents, and if it's at the bottom, that's to the children. Then what you can do is you can say the probability of y w, so g of x. So you can basically here do what? You can remove w do x. You can remove the z. Oh, I see. Okay. Oh, sure, because it's conditionally independent of it. Okay. So we can also ignore the active intervention. So we can ignore a do if probability of y given w do x do z, if we have a graph where we remove all the outgoing, the edges coming from the parents of x to x, and then all the edges coming out from the children of z, then we can write this simplification. And we can ignore an intervention variable entirely. Oh, wait, I forgot the then. Yeah. Okay. So back to basics, right? So at the end of the day, when you're thinking, I'll just do a quick summary, and I think we can move on. So when you're trying to basically, generally, like when you look at the laws of probability, we have stuff like Bayes' law, right? So we can say probability of x given y divided by the probability of x times the probability of y. Did I mix it up? I'd be very embarrassed if I did that. Wait, no, so it's probability, sorry, probability of x. Yeah, sorry, I wasn't clear. So ignore this, ignore this. So the probability of x, okay, yes, sorry, I got confused. The probability of x given y is equal to the probability of xy divided by the probability of y. So this is the definition of conditional of uh, of a conditional distribution. But the probability of x given y is also equal to the probability of y given x, and by the probability of y times the probability of x. So we have like Bayes' law, and then we have normalization, and we have conditioning. And these are generally the rules that let us work with probability distributions. But when we're adding like when we're adding these do interventions, there's also three additional rules that may help us. So the first one is when can we ignore observations given separation. The second is when we can ignore an intervention. So basically turn an intervention, let's say like do z, into a regular observation like z. And when can we ignore an intervention completely? So the main idea here is to essentially look at subsets of the causal diagram with incoming or outgoing edges removed. And then we can use these rules to be able to make certain inferences. They don't work over all graphs, but they work over a bunch of graphs. And it is, at the end of the day, it seems like an iterative and meditative and intuition heavy process that I don't think machines will be able to encode anytime soon. But if you do have expertise in these things and if you're making policy decisions, it certainly seems to be helpful. All right, so I want to let me briefly talk about this article because I think this is sort of the part two. So I think I was sort of thinking about, so I've played a lot of Dota at this point, like it's like an insane amount. But I also grew up playing a lot of chess, and one of my observations was people would tell me like, "Oh, like you play chess, so you must be like a strategic person, and you can make like decisions very well." And I actually never thought that was particularly interesting because you don't actually make interesting decisions. Like what chess tests you on is, like how good you are at chess. It's a bit like the SAT. It's like, can you prepare an opening? Can you improvise a bit in the mid game to play interesting moves? And then in the end game, can you close? Like, can you execute on like a long, winded, very precise plan? But you're not working with other players. Like your pieces aren't like telling you to fuck off, for example. So it's not at the end of the day, and like they don't have their own wants and needs. But I think Dota is a bit more interesting in this regard because it's a 5v5 game. It has fog of war, it has shared resources, and you all have a common goal, and you have to sort of organize yourself around achieving this common goal, just destroying the enemy ancient. And the way you do this is you have to convince four people you've never met to trust you for about an hour and to help you overcome a difficult opponent. And so none of this is really interesting. Like in the case when you're winning, like when you're winning, none of the below matters. But when you're losing is when you need to step up. And the reason that's the case, like it's like when teams are winning, like they're very positive. Like they're very friendly. They tell each other good job all the time. People are laughing. They're memeing. They're picking interesting item builds. But when they're losing, they start getting mad. They start blaming other people. They start swearing. They start like being negative. They start like being hopeless. So this is when I think stepping up and being like a good leader really makes sense. Because if you're gonna like basically the algorithm, the way it works is it matches you against people that have roughly your same skill. So you're basically have like a 50% chance of winning, or at least that's what the algorithm optimizes for. So if you're really just going to win easy games and lose hard games, then you're basically going to stay at your exact same level. So it's only by winning hard games, I think, that you've become a better player. So I think one thing I noticed a lot is people complaining about, like, why does my team suck? And I noticed one thing I always found funny was, like, if you've played 20 games and every team you have sucks, maybe you should consider whether you're the one who sucks. And I think blaming your team prevents you from stepping up, like prevents you from being the one who actually carries your team. So again, like, you don't pick your teams generally in the real world. Like, I mean, if you're recruiting people, you do. But even then, you're not like recruiting the ideal people join you. You can only recruit the people who also want to apply to you and the people who are willing to join you and sign an offer and have like this specific set of life circumstances to join you. And so blaming doesn't help. And so I think when you're losing, it's easy to be positive, and when you're winning, when you're winning, it's easy to be positive. And so again, I think when you're on a losing streak and you find yourself having this attitude of blaming others or blaming your situations, I think you're generally burnt out. Like a game's supposed to be fun, and I think to some extent work also should be somewhat fun. And so it's better to find a new game to play. So another thing I noticed is communication, where basically I've heard this a lot, like where people, like, let's say you're losing, and people die a lot when you're losing, right? And people, someone will go on chat and will say, guys, like, stop dying. And this is just absolutely useless feedback, because, like, I mean, no one wants to die. Like, I want to win, right? Like, that's why I queued. That's why I'm queuing rank, because I want my rank to go up. I want to feel better. I want to get the status that comes with having a higher rank. So I think it's much more challenging, but much more useful to say, well, okay, guys, like, for example, like, we're getting really screwed by their Earthshaker. Maybe we need some more magic immunity. So we need to, get our Black King bars. So, okay, so we need time to farm it. Therefore, we need more vision so that we can farm more safely. So great, now you have a plan. And so this is much more difficult, but I think it's really what you need to do. And again, complex plans are brittle. So if you have a plan that involves 5 people orchestrating the usage of like 10 spells perfectly, that plan is gonna, like, I think there's like a famous Mike Tyson quote, like, everyone has a plan until you get punched in the face. Right? And I think this is why simple plans help, because you can sort of get to doing something reliable that works. And I think often being reliable is better than being perfect, at least when you're working with teams. So I think this issue of credibility is so important. Like, let's say you're just coming in and you're joining, like, 4 other players, and if you start like micromanaging them and telling them what to do, they're all going to be like, "Well, who the fuck is this guy? Like, why is he telling me what to do?" And I think your teammates, what you have to understand is that your teammates will only listen to you if they perceive you as being the best player on the team. So if you are destroying the enemy team, people listen to you. The flip side of that is that if you're playing with someone and they're 1v5ing the enemy team, just acknowledge that they're a better player than you and you should listen to them, and you have more to learn from them than they have to learn from you. It's a very bitter pill to swallow, but it helps you get started. And also, I think crybabies get muted. Like, back to this whole giving non-actionable feedback kind of thing. If you're just crying like, why aren't you guys doing this? Like, why aren't you guys doing that? Like, people just mute you and people stop listening to you, mentally tune you out. So the analogy to stop work is like people stop answering your emails, or they won't value your feedback that much in meetings. Maybe eventually get fired. But generally, being a crybaby doesn't help. I think like observing that a problem exists, but also having a solution for it is much more valuable. So similarly, like, when you're giving feedback, I think positive feedback also needs to be very specific, because I've often like heard it's like, if you tell me like, oh, Mark is really smart, it's like it's great to work with him. That's not actually that great feedback when you think about it. Like, a better thing to say was like, well, if it wasn't for Mark, this project would have failed. He really brought it back from the dead. Like, we owe him the life of this project. That gives me a brand. It's much more useful feedback. People can have a one-liner to know that I'm smart. So that's much more valuable. Similarly, for negative feedback, I think what you need to do is make it a we. Like, if you just sort of, let's say someone's having a bad day, right? And then you sort of start picking on them and you go like, why did you do this? Like, that was a mistake. Like, they know it was a mistake, right? Like, they died. Like, they know that their decisions making wasn't ideal. So even giving this general feedback is like, well, like, this enemy is really strong at this point. We need to avoid this. We need to capture this. Making it action was much more useful. So I think the last thing I want to talk about is like nerves. And I think this is, I think, the number one reason why I see people lose a lot of Dota games. So there's this meme called Tiny Airline. So there's this hero called Tiny, and what this hero does is he can toss enemies. So generally, you want to use it. Like, let's say you want to toss an enemy into your team, and then it makes it very easy for everyone to gang up on this enemy and just kill them very quickly. And so if it's a very valuable enemy hero, like a carry or something, or like a key support, it's going to be huge. So what some players will do is like they'll pick tinies and then they'll start throwing you onto the enemies repeatedly, and there's nothing you can do about it. You just like keep dying because this other dude is tilted. And they do this for like 40, 50 minutes at a time, and you're just thinking like, oh, why did you queue? Like, why are you here if you're this mad and if you obviously had no interest in playing? And so I think this is where cooling off really matters. Like, let's say even if you just go to the jungle and farm and do nothing for 10 minutes, that's fine. And I think some people are lost causes. Like if you play with a player like this, you'll realize very quickly that the more you tell them to stop, the more they keep doing it. And so just ignoring them is often the best strategy. Just pretend like they don't exist, and then eventually they'll realize why am I throwing a bunch of pixels to make myself lose for 50 minutes? Like, this isn't fun. The flip side of that is if someone is apologizing a lot for their misplays, like they're being like very sad, and you feel like they're having a hard time. Often they want to win, but they're having a hard time, I think, in real life. So be extra supportive and acknowledge when they do good plays, so that they can feel like they're in a better mood, and at least they're judging themselves harshly enough. They don't also need their team to be judging them. So I think I'm still the article is still not done yet, but I think I do want to publish it probably in the next like week or so. But if you've worked on a team or have been a manager or led a team or have been led by a manager and some of the stuff really resonates, please let me know, because I definitely want to hear more about your experience. So yeah, that was it. So let me know if you have any questions. I'm gonna keep the stream on. I'm gonna take a quick 1 minute break. I'm gonna get some tea. I'm gonna go use the bathroom, and I'll be back to play the forest. So that should be fun. So let me know. So post your questions in the chat below. Please post a lot, make me feel good, and then I'll come back and answer.